Hello everyone, welcome back to my channel. In today's class, we will discuss Gauss's theorem in electrostatics. Before understanding Gauss's theorem in electrostatics, let us know what is electric flux. Electric flux due to an electric field E vector through a surface area capital S is defined as the total number of electric lines of force passing through that area normally. That means if we look at the diagram, and S is a surface area in the diagram, ds is a small part of the area capital S, and E vector is an electric field crossing the surface area capital S. Then mathematically, electric flux through a surface S is given by integration over the surface S E ds cos theta, or it is represented as integration over the surface S E vector dot ds vector. Here ds vector is the area vector for the surface ds, and we can see here that the electric field vector and the area vector, they are making an angle theta with each other. After knowing the idea of electric flux, let us now look at the definition of Gauss's theorem in electrostatics. Gauss's theorem in electrostatics states that the total electric flux through a closed surface is equal to 1 by epsilon naught times the total charge enclosed by that surface. Mathematically, it can be represented by the expression integration of S E vector dot ds vector is equal to 1 by epsilon naught multiplied by summation over all charges inside the closed surface. If we consider a closed surface, and that closed surface is denoted by capital S, and let ds is one small surface area on that closed surface, then the Gauss's theorem in mathematical form is given by integration over S E dot ds is equals to 1 by epsilon naught multiplied by sum of all the charges enclosed by the surface capital S. So after the definition, let us now understand Gauss's theorem with the help of one diagram. In the diagram, we have considered one arbitrary surface area denoted by capital S, and a charge small q is enclosed by this surface area S, and ds is one small section on this surface area S, and ds is shown in the diagram by the shaded portion. Now, due to the charge q, electric field is capital E vector, and on the surface ds, the electric field is directed as shown in the diagram, which is outward, and the magnitude of the electric field is given by 1 by 4 pi epsilon naught q by r square, and in terms of the vector form of the electric field, we can write it as E vector is equal to 1 by 4 pi epsilon naught q by r square into an unit vector, where an unit vector is an unit vector along the direction of capital E vector. Therefore, if we put the value of magnitude of E vector given by 1 by 4 pi epsilon naught q by r square, then the total electric flux passing through the closed surface is given by integration E dot ds is equal to integration 1 by 4 pi epsilon naught q by r square and unit vector dot ds vector, where the integration is over the whole closed surface area S. And simplification leads to integration 1 by 4 pi epsilon naught q by r square ds cos theta, because the angle between the unit vector n and ds vector, which is the area vector of the small area ds, they are making an angle theta as shown in the diagram in the previous slide, and therefore the expression for total electric flux simplifies to the form q by 4 pi epsilon naught integration over s ds cos theta by r square, and that may be written as q by 4 pi epsilon naught integration over s d omega. Here d omega given by ds cos theta by r square is the solid angle subtended by the small surface area ds at charge q. Now integration over s d omega, that means the summation over all possible values of the solid angle, is given by 4 pi and is denoted by omega, is the total solid angle subtended at charge q by the whole surface area S, and the total charge enclosed by the surface is here small q, and therefore the electric flux becomes integration S E dot ds is equal to q by 4 pi epsilon naught into 4 pi, and that is equal to q by epsilon naught, and that is equal to 1 by 4 pi epsilon naught multiplied by the charge enclosed by the surface. And this is the general form of Gauss's theorem, where q is the total charge enclosed by the surface. This is the proof of Gauss's theorem.